All right, so we're going to be talking about the solubility of ionic compounds and specifically sort of quantifying that solubility. In your previous semester, you would have talked about solubility in this sort of very black and white sort of way. All right, you would have been using this particular table here, this solubility table. Okay, so just for the sake of getting our iClicker participation, let's see who remembers this. We'll do a poll. And we can say that I remember this table. Can't spell this morning. And B, no clue. Let's see. All right, awesome. So this table right here was how you would be looking up whether a compound was soluble or insoluble. So given something like NaCl, we would try to find these ions on our table. For this particular one, we could actually find both the sodium ion. This tells us that sodium compounds are soluble and that there are no insoluble exceptions. Or we could look up the chloride ion, and this says that most chloride compounds are soluble unless it's paired with silver, mercury, or lead. And of course, sodium chloride is sodium and chlorine. So that's how we could determine that this was soluble. Likewise, if we were given something like barium sulfate, we could again try to look this up on our table. We see that most sulfate compounds are soluble, but one of the exceptions is barium sulfate. So this would be insoluble, right? And the world was sort of divided into these very black and white kind of things, are either 100% soluble or 100% insoluble. Okay, and what we're going to see is we're sort of going to build off that, where that wasn't quite the truth. All right, we still are going to consider our soluble compounds to be, 100% soluble. All right, these are kind of analogous to our strong acids in the sense that if we have a soluble salt, we're going to assume it completely dissociates when you put it into water. Right, but if we have something like barium sulfate, we used to say that that was insoluble, and we're going to see that it is pretty insoluble, but now we're going to be able to quantify exactly how much of the barium in sulfate will dissolve. It's only going to be a little bit, but how much, right? So this is not 100%. This is what we're going to say now, be slightly soluble. And exactly how much?
This is the pre-lab lecture.
Yeah, so let's mute. All right. Cool. All right. So how are we going to do that? Well, so now we're going to have this new addition to our constants page. These are these Ksps, these solubility product constants. And so now if we were to look up our barium sulfate, we would have this Ksp value associated with it. That's going to help us quantify the degree to which this compound is indeed soluble, right? And again, it's not going to be very much, but we're going to see how much of these barium ions and sulfate ions are able to dissolve in solution. All right, so that's the name of our game. These previously insoluble compounds, now we're going to have these list of Ksps, and they're going to help us determine the exact degree to which these will dissolve in water. Again, it's not going to be much, but that's going to be the name of the game here. All right, so step one. Let's do it on it. Let's sort of work through an example problem here so we can see exactly how. All right, so 0.1 moles of barium fluoride are added to water. what is the concentration of barium ions? Let's start there. We're going to start with the easiest of the two. Okay, so step one, and this is very similar to what we saw before when we were doing our acid-base equations for titrations. We need to start with a balanced chemical equation. All right, and this is going to be for the solubility of barium fluoride. So we're going to take our barium fluoride, which is a solid, and we're going to add it to water such that it dissociates. And I shouldn't use those one-headed arrows because, in fact, this is quite in favor of the reactants. It will dissociate into the barium ion, which is aqueous, and 2 fluoride ions, which would also be aqueous in that solution. Okay. So one of the things that we're going to have to make sure we remember back from first semester is how the heck did I get these charges on these ions, right? Starting with that barium fluoride formula. Remember, for many of these ions, we can determine their charge based on where they live on the periodic table. So if I just pull up a periodic table real quick, there is one. Right, we can ignore all this. Everything that lives in this first column forms a +1 charge when it makes an ion. Everything in the second column is +2. If we jump to the other side of the periodic table, noble gases don't form ions. The halogens form ions with the -1 charge. Everything in this column, -2, and everything in this column, -3. The not the halogens, I'm sorry, the transition metals, you need to figure it out from the formula. All right, we got to know the charges on those ions, right? That's how we're going to write our balanced chemical equation correctly. Okay, and then equally, almost more importantly, is how I got my balanced chemical equation. I included these 2 fluoride ions because there are 2 fluoride ions in every barium fluoride, right? So I had to make sure that chemical equation is balanced. All right. So balanced chemical equation, check, check. Step 2, again, we need our equilibrium expression. And when we think equilibrium, what do we remember? What over what? Products over reactants. All right, and so for our Ksp, this is now what we call this equilibrium constant for this particular solubility reaction, right? For acids, it was a Ka. For bases, it was a Kb. For these solubility products, it's a Ksp. And we're going to do our products, the concentration of barium times the concentration of the fluoride ions. But remember, because this is not just fluorine, but in our balanced chemical equation, there are 2 fluoride ions. I have to square that term in my equilibrium constant. Okay. Now, normally you would put this over your reactant, BAF2, but this thing is solid. It is not in solution. So it's not dissolved to the point where it even has a concentration. So for Ksps, it's just the product of those 2 products, the product meaning the multiplication of those 2 concentrations of your product. And you're not going to forget that if you have a coefficient in your balanced chemical equation, that needs to become an exponent in your equilibrium expression. All right, so now we're going to build our ice table, right? Because this is how we fill in. So step 3, build an ice table, because that's how we fill in our equilibrium expression. Again, my barium fluoride is going to start out as that 0.001 moles, but honestly, I don't even have to worry about it because it's not going to factor into my equilibrium expression. I'm going to keep it there just because I think it might help see how these other two expressions I get. Okay, so concentration here, concentration there. Okay. Now, what's the change going to be as my barium fluoride dissociates into solution? I'm going to decrease the amount of reactant that I had, that solid barium fluoride, and I'm going to increase my products, right? So my barium ions are going to go up in solution or up in concentration. Okay, and for every one barium fluoride, I will get one barium ion because that's that ratio in my balanced chemical equation. They're 1 to 1. But now when I get to my fluoride ions, start out with 0 of those. But for every barium ion that dissociates, for every barium ion that dissociates, I actually get 2 of my fluoride ions. So if my barium fluoride is decreasing by X, the fluoride concentration is going to be increasing by 2X. Okay. So this is the 0.100 minus X, but again, this isn't even going to enter into our Ksp term. But the barium concentration is X and the fluoride concentration will be 2X. So then plugging this into my equilibrium expression, I'm going to scrunch this up just so I don't run out of room. I get Ksp equals X times 2X squared, right? Make sure that you can see how I got that 2X squared because the concentration of fluoride was that 2X. And when I plug it in here to my Ksp expression, that concentration of fluoride ions is squared. And then how am I going to go about finishing this off? In order to do this, I just need that Ksp value. Where can I find that? From my constants page. All right, so we just have to use our constants page in order to look up the Ksp for the compound that we're talking about, which is in this case, this barium fluoride. So 2.45 times 10 to the negative 5. All right, so everybody take a minute and give me what the concentration of barium ions are when I add this barium fluoride to water. Where's my calculator? We'll do 3 sig figs here. So I'm just going to sort of focus on my algebra here. What I get is I got to distribute that squared in there. So I get 4x cubed equals that 2.45 times 10 to the negative 5. So then I got to divide both sides by 4. That cancels it out over here. And then in order to get X, I'm going to have to take the cubed root of both sides. All right, so I'll give you another 30 seconds here to finish this off. All right, and we get that our concentration is 0.0183. And importantly, as I've sort of said before, it's easy to forget what it is that you're talking about here, right? So specifically X was that barium concentration, right? So what is the concentration of barium? That's what I was originally asking. That would be that 0.0183 molar. All right. But now what if I had instead asked you what the concentration, what's the concentration of fluoride ions? Yeah, I will. Give me 1 second. All right, so importantly, when we're talking about the concentration of fluoride, fluoride isn't just X, fluoride is 2X. So I'd have to take that same value that I got for X and multiply it by 2 in order to get my fluoride ion concentration. So that would just be double the concentration of barium ions, or 0.0366 molar. All right, but so that's what our Ksp is doing. It's relating the concentration of these ions at equilibrium for relatively insoluble compounds, right? Concentration of 0.0183 molar isn't anything crazy. It's a fairly low concentration, but we can see that it's not nothing, right? Previously, we were treating these insoluble compounds as if they didn't dissolve even a little bit. We see that that's not quite true. They do dissolve to some extent. All right, and then yes, question about how you enter this into your calculator. Some of you are going to have a button that looks like X in this little divisor sign here, and that would allow you to plug in any variable here, right? So in this case, it's the cubed root, so you would put a 3. The other thing that will also always work for everybody, and this is a little bit weird, but when you're taking the root of something, this would be equivalent to, if I did into my calculator, 2.45 times 10 to the negative 5 over 4. And then I put this in parentheses and raised it to the power of 1 over 3. All right, this is something that's a little bit weird, and I'm not going to get too far into it, but it's definitely something that you would learn in an algebra course. But it turns out that a cubed root is the same thing as raising something to the power of 1 over 3. Taking something with the root of 4 is the same thing as raising it to the power of 1 over 4, et cetera, right? So taking something to the xth root is like raising it to the power of 1 over x. So depending on your calculator, I know that this works a lot more often. Calculators, some of them don't have this button here. I know like Excel, which is like what I use as my calculator, doesn't. And so I have to raise something to the power of 1 over x, and that's how I do it in my calculator. All right, it will be fairly important for this particular section because as we saw in this one, we have these exponents up here, and we're going to see that a lot. All right. So real quick, before we sort of move on with the different type of problem that we can expect here, let's do one more of these KSPs. Let me do a good one though. There we go. Calcium phosphate. All right. So I want you to give me the balanced chemical equation and the Ksp expression for when we take calcium phosphate and add that to water. Okay, let's make sure that we can do those two basic steps or we're going to be in trouble. All right, balanced chemical equation and the Ksp expression. All right, so let me just point something out real quick. So this one, because there were these, the fact that I had three calcium ion or three calciums in my formula means that I'm going to need that coefficient of 3 out front when I do my balanced chemical equation. All right, and that's going to turn into a coefficient of 3 for that calcium in my Ksp expression. Likewise, in my formula, I have 2 phosphates. That means I'm going to have 2 in my balanced chemical equation, which is going to turn into this exponent of 2 in my Ksp expression. All right, so just make sure sort of goes back to prior to when I came here, just building equilibrium expressions. Make sure that you can understand how that is. And if not, you want to go back and review how you just build equilibrium expressions, period, right? Importantly, these coefficients in my equilibrium or in my balanced chemical equations become exponents in my equilibrium expressions. Okay, so now we're actually going to go back to our calcium fluoride example, and we're going to explore something that's called the common ion effect. Okay. Actually, probably gonna need more room. Okay. So now we're gonna explore the solubility of our solution that we started with, which is again that barium fluoride, in a 0.100 molar solution of sodium fluoride. Okay, so now we already have this solution of sodium fluoride. And if we go back here, we can kind of convince ourselves that sodium fluoride, would be a completely soluble solution because sodium's always soluble with no exceptions, right? So if I add sodium fluoride to water, 100% of it is going to dissociate into sodium ions and fluoride ions. Right, so now I have this barium fluoride, which is not very soluble, and I'm going to try to dissolve it into a solution that already contains a bunch of fluoride ions, right? This is this idea. So if I have this solution of sodium fluoride, that means that I'm starting out with an initial concentration of fluoride ions equal to this 0.001 molar. And as you would expect, given our balanced chemical equation for the dissociation of barium fluoride, we already did this one, so I'll just put it down quickly. We've got a barium ion plus 2 fluoride ions. right? And exactly what you would expect from Le Chatelier's principle, if we increase this concentration of fluoride ions, that's going to shift this equilibrium back in favor of our reactants. So what the common ion effect is if we already have a solution containing those ions, we're going to see that this equilibrium is shifted back in favor of these reactants, meaning that this is going to be even less soluble than it was without those fluoride ions present, right? So we're going to get even less barium fluoride to dissociate under these conditions. So the common ion effect, we're just going to summarize it real quick. This is insoluble compounds are even less soluble in solutions containing common ions. Meaning ions that they have in common. All right, and let's just go ahead and establish this mathematically using our equilibrium expression. So this was our step one, our balanced chemical equation. Step two was our Ksp expression. And then what do we use to fill in our Ksp expression? We're going to build an ice table. Okay. Again, I don't really have to keep track of it, but I think that maybe it kind of helps to just see it up there. So again, my initial concentration, and I guess I should state this. Let's finish off this problem. Solubility of 0.1 moles of barium fluoride in a 0.1 molar solution. So again, I'm going to start out with some amount of my barium fluoride here. It really doesn't matter the amount. This is one of the interesting things about these solubility products is it doesn't matter how much you start out with, you'll always get the same equilibrium concentration of those two ions, as long as you have enough. And since the solubility of these compounds is so little, you really don't need much in order to get that saturation, all of it, all ions dissociated as possible, right? So the highest concentration of barium and fluoride that you could get. So I'm going to start out with 0 of my barium fluoride, but now I'm going to have this initial concentration of fluoride ions here. My barium fluoride concentration is going to go down as it dissociates into barium ions and into 2 fluoride ions. Okay. So now I get for my overall, but again, this doesn't appear in my equilibrium expression. I get X, and now I get 0.100 plus 2X. So plugging all this into my Ksp, again, let me scrunch this up so I got some room. We get that our Ksp is equal to barium concentration, which is X, times this 0.100 plus 2X squared. Okay. And this is again equal to that Ksp, which I can look up for my barium fluoride. We already looked this one up, so you might have already had it down, but that's that 2.45 times 10 to the negative 5. All right, that's our Ksp for barium fluoride. Okay, so now we're in this situation here where we're going to solve our equation for X again. Again, we're going to employ an assumption that we've been doing all along, which is that since X, we know X is going to be so tiny, this 0.1 plus 2X is essentially just going to be equal to 0.1, right? And again, with our fancy calculators, we should probably just start teaching all how to use your fancy calculators a little bit better, but because this is the way the course was designed, I'm going to stick with it, that this is really just going to be an assumption that makes our lives easier in terms of the algebra. So we get X equals 0.100 squared equal to that 2.45 times 10 to the negative 5. All right, so let me just change the format of this number. All right, so if we solve this, we get that X, whoops, whoa, just happened. We get that X, which was our barium ion concentration, is equal to 0.00245 molar. Okay, and just comparing that to what we got originally, our concentration of barium when we had no other salt in there was 0.0183. Now we can see that we got a much smaller number for the barium concentration, right? So because of that common ion effect, because we already had some fluoride ions in there, we see that we get a much smaller concentration of barium that actually dissolves in solution. Okay. It's only about 13% of what our original number is, right? So almost a full 1/10 less barium dissolves in solution because of that common ion effect. All right. So if we look at our Ksp, so first of all, let me just remind everybody what Q is. Q is value of the equilibrium expression outside of equilibrium. So what the heck do I mean by that? Okay. Let's say whoa. Okay, so one of the first reactions that you would have learned about were these precipitation reactions, where if you have these two solutions that mix together that form an insoluble product, that insoluble product will precipitate out. And again, now we're going to extend this concept of being an insoluble product in terms of our actually quantifying it using these Ksp values. Right. So if I took a solution of 1 liter of 0.1 molar sodium fluoride, which is soluble, so it's going to completely dissociate, with 1 liter of 0.1 molar barium nitrate, which is again completely soluble, so it will dissociate. And we want to know, will the BAF2 precipitate? So we know our Ksp expression is the concentration of barium times the concentration of fluoride squared, right? And that will equal that Ksp value at equilibrium. But in order to get the value of Q, I'm going to use this same expression, but I'm going to plug in these concentrations here, which are not equilibrium concentrations, right? This is before I've accounted for any reaction that's occurred. So now I'm going to take my, and it's actually going to be 0.100 moles divided by now 2 liters, right? So I have to account for the fact that my volume's changed. Times 0.100 moles over 2 liters squared. Okay. So plug that in, and that will give me the value of Q, which is this 1.25 times 10 to the negative 4. Right? It's not equal to that Ksp expression because I'm not at equilibrium here. I'm outside of the equilibrium. And what we can see is that Q is greater than Ksp, right? And what this means, if Q is greater than Ksp, those concentrations are too high. They're not as low as they would be for our equilibrium value. So if Q is greater than Ksp, we will see precipitation. So in this case, yes, I will see precipitation of my barium fluoride because those concentration values are too big. Q is greater than Ksp. If Q is equal to Ksp, then I'm at equilibrium. So I won't see any change. If I added even a little bit more of either calcium or fluoride, I would start to see precipitation. But if Q is equal to Ksp, those concentrations are sort of perfectly what they can be. Can't get any higher than that, but they're at equilibrium. And so then finally, if Q is less than Ksp, that means your concentration of ions is low enough that you won't have any sort of precipitation. So no precipitation. All right, so those are the relationship between Q, which is again, just when you start plugging in values to your equilibrium expression, even though you're outside of equilibrium. And we have this relationship where if Q is greater than the Ksp for a compound, that's under the conditions that we will see precipitation. We'll see solid barium fluoride start to form in such a way that we get enough of it that forms that the concentrations of barium and fluoride decrease, right? Barium ions and fluoride ions start to decrease. All right, so then the last thing that we're going to do is we're going to look at these mixed ion solutions. All right, so what does this look like here? Let's say we're going to have a solution that has a concentration of barium equal to 0.100 molar and a concentration of calcium equal to 0.100 molar. All right, and we're going to titrate fluoride into this solution. So whoops. All right, so we have this solution that contains a mixture of barium and calcium, and we're going to start adding fluoride ions. And we want to know what is the concentration of fluoride ions at which the first metal will start to precipitate. Okay, so if we get our equilibrium expressions, or rather our balanced chemical equations, get our barium fluoride. This is our same one that we've had. Gives us our barium ions. Plus 2 fluoride ions. We get something very similar for calcium fluoride as well. Oops. Gives us calcium ions and 2 fluoride ions. Okay, and so then for each of these, we can get our Ksp expression. All right. Now it says, what is the concentration of fluoride ions in which the first ion, and specifically, I mean, the first metal ion will start to precipitate? Okay, so the question is, which is going to precipitate first, barium fluoride or calcium fluoride? Okay, let's go back to our Ksps. And I want everybody taking a look at these Ksps. I want you to answer with your clicker whether you think that it's going to be barium fluoride that precipitates first. That'll be option A. Or calcium fluoride that precipitates first. That'll be option B. Which one of these is going to precipitate first based on these Ksp values? Okay, JK. All right, let's give it a shot. Said it didn't like the other one. Let's see if this one works. All right, I think it's good. All right, so A is barium fluoride is going to precipitate first, or B is that calcium fluoride is going to precipitate first. All right, I'll give you another 15 seconds to put in your guess here. Which one is it going to be? Calcium fluoride or barium fluoride? Which precipitates first? All right, so indeed, it is calcium fluoride that precipitates first. How do we know that? So I'm going to compare these two Ksp values here. I see that calcium fluoride is a much smaller value for its Ksp than barium fluoride. And remember, these Ksps are the product of those two ions in solution, right? The concentration of those two ions. So lower Ksp means that the concentration of ions is going to be much less in solution, right? So the lower the Ksp implies less solubility, which implies it's going to precipitate earlier. Can't spell this word today. Right? calcium and fluoride, those two ions concentrations are going to be very, very low. And then before it starts to precipitate, right? So that calcium fluoride will precipitate earlier than the barium fluoride because that Ksp value is smaller. Right, so I know it's going to be the calcium fluoride that precipitates first. What was that value again? Sorry. 1.46 times 10 to the negative 10. And it wants to know what the fluoride ion concentration is going to be when that calcium fluoride starts to precipitate. I know what my calcium ion concentration is, right? So then I'm just going to plug in here and rearrange for the value of F. Here, I'm about to make a mistake. Right, so I know my calcium concentration is this 0.100 molar. I don't know what the fluoride ion concentration is. That's my X. But I know that the product of those two together is going to equal this 1.46 times 10 to the negative 10. So I can solve for X equals the 1.46 times 10 to the negative 10 divided by 0.1. And I'm going to take the square root of it or raise it to the 1/2 power. I'm pretty sure everybody's calculator has a square root button, but nonetheless. Okay, and that gives me a fluoride ion concentration of 3.82 times 10 to the negative 5 molar. All right, we could ask the same thing. What is the concentration of fluoride when the second ion precipitates? I'm just going to abbreviate it PPT. All right, so now I've added fluoride, I've added fluoride, I've added fluoride. At what concentration of fluoride ions will my second ion start to precipitate? Well, my second one is going to be the barium fluoride here. So I'm going to look up the Ksp value for that. That was that, what was it, 2.45 times 10 to the negative 5. Okay, I'm going to make some room here. Now I'm going to use my Ksp for barium. I know that my barium concentration in my solution is already this 0.001 molar. So now I'm going to solve for my fluoride ion concentration. I'll leave that as X equals that 2.45 times 10 to the negative 5. Okay, solving for X. Again, going to get a very similar expression, but now I'm just using that different Ksp value. And this gives me an X of 1.57 times 10 to the negative 2 molar. So we see that because the concentration, or rather because the Ksp was much larger, we have to get to a much higher concentration of fluoride ions before that before that barium fluoride will start to precipitate. All right, so just to sort of make some room here, let's look at these two values next to one another. At what concentration of fluoride does my first ion precipitate? that was quite low, 3.82 times 10 to the negative 5 molar, compared to the concentration of, right, so that's the concentration of fluoride ions, compared to the concentration of fluoride ions when that second ion starts to precipitate. Now it's much higher at 1.5, not 5.2, sorry, 5.7 times 10 to the negative 2 molar, right? I had to get to a much higher fluoride concentration to start precipitating the barium fluoride because the Ksp was much larger. Okay, just going to make some room here, because then the last thing that can be asked is, okay, so I know what concentration fluoride is going to be when the first ion starts to precipitate my calcium. I know what concentration of fluoride is going to be when my second ion starts to precipitate the barium. Well, what is the concentration of that first ion, calcium, when that second ion, the barium fluoride, starts to precipitate? Right, so I'm essentially asking how much calcium is left over, because I've added a bunch of fluoride and calcium started precipitating first. Right, so as I've added fluoride, I'm adding fluoride, I'm adding fluoride, I'm adding fluoride. Those calcium ions are then getting pulled out of solution. They're precipitating with those fluoride ions. And a bunch of calcium is going to end up reacting, forming calcium fluoride, as I continue to add those fluoride ions. And now I've finally added enough fluoride ions where the second ion starts to precipitate. Well, then how much calcium is left over, right? How much of that first ion is left over now that my fluoride concentration has gotten to a point where it's so high? So again, we're going to use our Ksp expression for calcium fluoride. But now what we don't know is our calcium concentration. And what we do know is the fluoride ion concentration when the barium fluoride starts to precipitate, because that's what we just solved for up here. So now we're going to be plugging into this expression, the 1.57 times 10 to the negative 2. And then we're going to square it because it's squared in our equilibrium expression. This is equal to the Ksp for calcium fluoride, the 1.46 times 10 to the negative 10. And what I get is my concentration of calcium ions, my X value, is equal to 5.96 times 10 to the negative 7 molar. Okay, so that's the concentration of calcium when the second ion, the barium, starts to precipitate. Right, and considering we started out with a concentration of calcium ions that was initially 0.1 molar, now we're all the way down to 5.96 times 10 to the negative 7 molar. This is like a ridiculously small concentration of calcium that's left over. Right, I've used up something like 99.9994% of my Ca ions have precipitated at this point. I really want to spell it precipitated. Precipitated. Right, so at that point where your fluoride ion concentration is large enough to start precipitating the barium, you basically have no calcium left over in solution. It's almost all been consumed by that precipitation reaction with the fluoride ions. Cool. All right. So we're gonna we got one more tiny topic to cover, and then we're gonna start in on transition metals on Wednesday.